welcome back. Hit that subscribe button if you haven't yet. But it's Mr. Hansen at Mr. Hansen 414, and we are here today. We're going to talk about transformations. So if you don't know what a transformation is, I got some news for you. You're going to learn today. So we're here rocking the Bumblebee, and we're going to talk about representing and describing transformations. So what does the word transform mean? Well, I instantly think of transformers. And in this sense, we are going to be talking about how to transform in geometry using rigid motion. So get ready for some fun. All right, guys, so here's what we're looking at. You're in your book, lesson 1.3. The essential question. We know that it's essential to know this. So this is like the big idea. How can you describe transformations in the coordinate plane using algebraic representations and using words? So by the end of this, that's the question you're going to be able to answer. So we got some vocab, and we got this idea that a transformation is a function. It can change the position, the shape, and or the size. So and or means it could just be one of those, but it could be combinations. The inputs are the points of the plane. So if you think of functions, we know that a function is the correlation, the mapping of an input to an output. So you put some points in, you get some different points out, they transform. And the words that we use is the preimage, so that's the initial figure, and what you get out is the image. So think of input, output, domain, and range. Preimage, image goes along the same kind of guidelines. The three types, so we don't have the Decepticons in this one. We got translations, reflections, and rotations. So this little rug, which should actually be a pretty flat rug, has all three. The tiles show all three. So we can use prime notation. No Optimus Prime around here. Got my boy Bumblebee. The transformation T moves point A to A prime. That just shows you that we're going from here to there, input to output. And if you use the function notation, which we might be a little more familiar with, so you'd have something like, the input is A, and you get out A prime. The T is the transformation. The word that we're going to use here is mapping. We're mapping from the pre-image to the image, from the old to the new. Cool. So you see here, this point A got transformed. Coordinate notation is a way, so we can use rules. Rules are nice. They're quick and dirty. We'll talk more about the actual movement soon, but let's just focus on the rules now. So find the unknown coordinates for each transformation and draw the image. Then complete the description of the transformation and compare it to the pre-image. So we have to make sure that we take our time here and do this correctly. So let's go ahead and do this. So we have the pre-image and we have the image. So you're going to take each x coordinate and subtract 4. You're going to take each y coordinate and subtract 3 for each point. So the first point is A, which is 0, 4. The rule tells you to get to A prime, you do 0 minus 4 and 4 minus 3. So the coordinates of A, you apply the transformation. So we end up with A prime being negative 4, 1. So we need to make sure we have that on our plane. Cool. B, so B is 3 and 0, so you can see that they substituted already. So when you do this on your own, I would highly recommend setting it up, make a little table, show your work by substitution. 3 minus 4 is negative 1, and 0 minus 3 is negative 3. So I can get my B prime, I should probably label these, right? That's A prime, negative 1, negative 3, that's my B prime, a B in my prime, 0, 0, origin, going down and to the left, negative 4, negative 3. And I see a triangle in my future. Which at first glance, I didn't recognize that the actual pre-image was a triangle because it was kind of right on that axes. So there you go. We have our new image. We transformed it from the pre-image. The translation. So we moved it 4 units to the left, 3 units down. Translation is just like sliding it, picking up and moving it. All right. Here's one that you guys should try. So I'm going to pause the video real quick so you can pause the video. So do what you got to do. Try this one. Hopefully you're still there. I went ahead and did this. So I did the math. And now remember, when you subtract a negative, you add the opposite. And that's why those x coordinates are all positives. You can see that we got our new shape. Now, the rule was to take the x and make it negative. So the reason why it went into quadrant 1 is because originally all the x's were negative, so now they're positive. So you could describe this, you could talk about it, but I think you guys are, I'm hoping you're doing all right. I feel good vibes. So you'll notice that that was not a translation. We didn't just slide it or move it. We reflected it. Like looking in a mirror, bouncing something off of a shiny surface. For this next one, you can see that this rule is different. There's a 2 in there as a coefficient, which means you're going to multiply. Generally, when you multiply things, they grow or they shrink. So I'm going to let you guys try this. Now take your time, plug in all the points, do the math carefully. So I'm going to bring you guys on to finish this off. You'll see that I plugged everything in. I'm setting up the math to go from j to j prime, k to k prime. The transformation is to multiply it by 2. So the image, we're going to get 2 times negative 1, which is negative 2, comma 2. 2 times 2 is 4, comma 2. 4, comma negative 4. We're going to plot those points and then compare it to our pre-image. So negative 2, 2 would be there. 4, 2 will be there. And 4, negative 4 would be there. So as you can see, we are going to have a much thicker guy, thicker triangle. We got our L prime, K prime. I don't know, can you see that baby crying upstairs? Wow, he's probably hungry. So this was a stretch by a factor of 2. So something to think about, number 2 in the reflection is for each transformation, what rule could you use to map the image back to the pre-image? So basically think about, like, put your equation brain on, like, well, how could you undo it? So if you multiplied it by 2, what could you do to bring it back? If you shifted it left or right, how could you bring it back the other way? Something to think about. All right, we got this concept of a rigid motion. Honestly, guys, rigid motion is huge. Get this down. Rigid motions, I always think of like old school video games with like, Super Nintendo, something like that, where you can only move in like up, down, left, right. But a rigid motion or isometry, which reminds me of like isomalts and like sugar cooking. I like baking shows, cooking shows. It's a transformation that changes the position, but it doesn't change the size of the shape. So for example, if I got a magic card, Snapcaster Mage, box topper. If I want to move this guy, I'll move him. He's in change size or shape. I can rotate him or reflect it, right? But it's still the same thing. So all of these shapes, it's important that we maintain rigid motion, and to do that, it preserves distance, angle measure, betweenness, collinearity, parallelism. Those are the 5 things of properties of rigid motion. At the end of the day, though, the shape's the same shape. It just is in a different place. So keep that in your head. Rigid motion, I'd make sure I get that down. So the betweenness and collinearity properties, it also preserves orientation. So the order of the vertices is the same, and it doesn't matter. Reflections don't preserve that, though. So basically, we have an example. We have a pre-image, and we have the image, and then you got the notation, the A prime, B prime, C prime. Use coordinate notation to write the rule that maps each pre-image to its image. Then identify the transformations. So like what actually happened. Later on, you'll have to do a combination of them. That gets fun. And confirm that it preserves length and angle measure. So that's the key. We have to prove that it maintained rigid motion. So there's a lot here, right? So let's just kind of look at it piece by piece. And if we first look at it, we want to find the pattern. So the x's, let's look at the x's first. Well, it goes 1 to -2, 4 to -2, 3 to 2. So I can't find like a math pattern. But if I look at the y's, 1, 4, 3, the x's, 1, 4, 3, the x's, the y's, they're opposites. They switch places essentially, right? So the opposite of the y coordinate, hit that subscribe button. See you later. So look at those signs changing, and then the y is the x coordinate. So just sit back and take a look, try to find the pattern. The transformation is going to be a rotation, and you can see that's a rotation of 90 degrees counterclockwise. I'll be honest, I mess up counterclockwise a lot, right? But like if we imagine a clock, clockwise is this way, counterclockwise is that way. So try to remember that. I messed that up a lot. Not enough clocks. Anyways, here's your original. Here's your transformed. The key part here, because we can claim and say, okay, it did this, it did that, but we have to prove it. So find the length of each side and use a distance formula to do that if you need it, especially if it's not on a horizontal or vertical axis. But if it's the same length, that means it preserved the length, which is a property of range of motion. So they find the length of AB, they find the length of AB prime, BC, BC prime, B prime, C prime, and on, and they all map out. They all check out, so we know it's the same shape. It preserves length. Now, this measuring of the angle, you should check it, but like, are you going to pull out a protractor right now? If you have one, go for it. If not, that's just something we're going to have to sum it. All right. Practice. I mean, the first thing I would do is ask myself, what does this look like, right? And it's clearly not a translation. Is it a reflection? Is it a rotation? It's got to be one of those, right? So I see the preimage. I see the image. It looks like the x's stay the same. Same. And the y's are the opposite. The op. Don't be an op. The transformation is a reflection, I think. Given by the rule, x negative y. So I want to make sure that we put that reflection is across the x-axis. So here's the x-axis, not straight, I'm sorry. But we've reflected it over the x-axis or across the x-axis. And then we got to check our lengths, right? We got to do our distance formula stuff. So, what's the length of PQ? You got to count it up. So count those squares: 1, 2, 3, 4, 5, 6. Do the same thing for PQ prime, P prime, Q prime. Too many primes. It's the same. So first one checks out. That's good. That's too much red on the screen for my eyes. Switch colors. QR codes. Well, we need to find out the coordinates. So QR, we had 1 and we got 3. And we got -4 and we got -1. Over here we got 3 and 1. You should do the math. I'm going to cheat a little bit because video time, but you should do this. And then we'll plug in for the PR and the P prime R prime. And we get -3. And we get -1. And we get -3. And you get 1. And you should get the vibe that it's going to be the square root of 25, which is a perfect square. And you should always simplify perfect squares. And preserves length. So we're on our path to range of motion. So you could make a statement that says something along the lines of, PQ is equal to P prime, Q prime. And they're basically comparing each of the line segments. QR equals Q prime, R prime. Same thing with P, R, P prime. The transformation preserves length. Pull out that protractor and move yourself along. So, now's a good time to kind of do some inventory, check on your notes, see if you're doing okay, see if it's feeling okay. You can go back to the first part and kind of compare for number 4 what if they're rigid motions or not. I think that's important to just identify. So here's some practice for you. Go ahead and make that happen. If you don't understand, these are great questions to email me or bring class. Throat's getting a little funky. You guys like I don't even know what to call this. I'm drinking some stash. I don't know. It's okay. So non-rigid motion. So we talked about being rigid. Now we're going to talk about being a little non-rigid. I'm going to break this video up into 2 parts. This will be the last part for this one. We're already about too long. So transformation that stretch or compress, stretch, compress. Not rigid motions, not the same distance. Fun houses are pretty fun. I don't know next time we're going to go to one, but it's a vertical stretch in the picture with the old girl. So we got coordinate notation. So you got to write the rule that maps the preimage to the image. So we're really focusing on the rule, right? The before, the after, the input, the output. And then we just got to make sure that it's not a rigid motion, and you have all those different ways to check that from the last one. So this I would get my little chart and check them. So we got the preimage. It looks like the x's all stay the same. I'm looking at the y's, 1 to 3, add 2, -1 to -3. I'm not adding 2 there. Multiplying by 3. And that's written right here. By the rule, they write it all out. The better you can describe. Some of you guys like to pull that common sense thing, and I get it, but we got to try to describe it the best way possible. And then they're going to head and they do the check. They do the rigid motion check. And think about it. If you multiply a side by a number that's not 1, it's going to expand or shrink, and it's not going to uphold the length. It's not going to uphold the length. Man, my daughter, she has an iPad, but the iCloud account's the same as mine. I need to make her own, but these kids be FaceTiming her all the time. It's like, man, leave me alone. My phone rings for it. So MNP, we're going to map pre-image to the image. I'm going to take a look, and what math, dog, I'm sorry, she distracted me. Looking at it, I see the x's are being multiplied by 2, right? So twice double multiplied by 2, whereas the y values look to be halved. They cut in half. So then our rules, this is a little funky, right? A little complex. 2x, 1/2 y. So we got to make sure that you multiply the x's by 2 and the y's by 1/2. After you do that, I'm just going to fill in the answer down here because I got to finish the thing, and this phone keeps vibrating, and I got to go tell my daughter to pick up her iPad. But you'll know, whoa, I don't know what that was, that the mn prime does not match up with the original. Therefore, it's not a rigid motion. So, the big takeaway here is if it's not rigid motion, it's going to look different. The size will be different. That's usually the best way to determine it. There are a couple other things, but the size doesn't change. The length doesn't change. A couple of your terms. Pause it. I'm going to write the rules for you guys just to make sure that you get them, but please pause right now so you don't cheat. Stop cheating. So this one's going to be 1.5x, 1.5y. Oop. And this one, number 9, is going to be 1/2 x, 3y. So there are your rules if you were stuck. Critical thinking. It's important to be a critical thinker. Nobody likes a dummy. A question to consider, guys, is, how are transformations of rigid motions and non-rigid motions similar and different? And, if you look at that chart, they're both of them preserve betweenness and collinearity. Rigid motions preserve the distance. Non-rigid motions don't. You guys should think about this. Oh, I surprised myself. This lesson was going to go further. So let's look at the homework. I'll assign these. I'll assign these, but here's your thing. Do your thing. Hopefully you got your books so you can draw these, because it's really hard to use without graph paper, because it's all really just algebraic stuff. We're doing geometry through algebra, which is how it should be. Trying to pause. So there's some more homework, guys. We're working on transformations. Feel free to wear a mask to class if it makes you feel better about your face. Unless you got a whole lot of money, you ain't gonna be able to transform your face. At least if you do, it'll be a rigid motion. To do what you want to do, it'd be a non-rigid motion. Look at that. So yeah, you're gonna do a bunch of this. I'm gonna tell you what to do. But hopefully that makes you feel like you know what's going on. Sorry, I couldn't see. Can't fit my glasses under there. So I would like real quick for you guys to come back up to where we started and ponder with me this essential question. So the essential question was to make sure that you guys are considering how to describe transformations in the coordinate plane using algebraic representations and using words. Come up with your own definition. It needs to stick, but you can use coordinate notation to write the rules, and it's going to describe how the preimage points are transformed to the image points, right? Your input output. And you can use words like reflection, rotation, translation, stretch, and dilation, right? Reflection, rotation, translation, stretch, dilation, rigid motion or not, transformations rigid or not. But yeah, so I think that you guys should be all right. And I wore a bumblebee mask, so the best you can do for me is hit that subscribe button and give me another subscriber. We're almost at 300. So Advanced Transform 4, I will see you later. Next time you'll get into mod 2, some more transformations.